So these are my reasons why I'm interested in prehistoric whale migration, but we really have to start with how in the world do you know anything about where a prehistoric whale was or was not migrating? So now we'll start talking about the hitchhikers, the heroes of the story. These are whale barnacles. I'm going to tell you a little bit about them. Really interesting critters. We don't know a ton about their lifestyle because they are very hard to study. But we do know a few things. They seem to only live for a few years. They attach to whales by growing and digging down into the skin. And conveniently, they have some high host specificity. So this top species that I'll talk about most of the night, Cornula diadema, lives solely on humpback whales. This other species, Cryptolepis rationecti, lives on gray whales. And that bottom species, Setoporus complanatus, lives on right whales. If you take a Cornula, flip it over, that's what it looks like on the right. So all of those pores or chambers that you see in life are full of whale skin, and prongs of whale skin will be running up all of these ribs that you see on the outside of the barnacle. So the barnacle is growing down, digesting the skin, and kind of molding it into these prongs that it's grabbing onto. As far as we know, the whales don't mind it, but they don't really have much of a choice. Faster than the whale could possibly shed them off, right? And as they grow, they are continually exposed to isotopes in the surrounding seawater, which are just different versions of atoms that differ in the number of neutrons. And when they're exposed to these isotopes, they're taking them up and incorporating them into their shell. And in this case, we're talking about oxygen isotopes specifically. We could talk about other isotopes for other matters. But they're taking up these oxygen isotopes, incorporating it into their shell, and the ratio of each type of isotope that they put into their shell will depend on how much of each isotope is in the water, and it will also depend on the temperature of the water. And all of those things come together to determine what the isotopic ratio of the shell is. It's defined by this nasty equation. This was figured out by J.S. Killingley in the 1980s. But all it really says is that barnacle shell isotopes depend on the seawater isotope balance and the seawater temperature. Okay? So, in theory, if you know what seawater isotope balance is and you know what seawater temperature is, you can then predict throughout the ocean what a barnacle growing in any region should incorporate into its shell in terms of isotope ratios. Okay? Or said another way, if you know enough about the seawater, then a barnacle shell holds some chemical clues as to where it has been or where it's been growing. All right? So that's where we're going to jump off into the real meat of the rest of the night. So I'm going to focus on basically just two brief research questions. Do barnacle shell isotopes reliably record whale movements? Meaning, like, if a barnacle is on a whale and we say that that shell can record information about the water it's been growing in, can it actually indicate where the whale has been going? And if so, what can we learn from fossil whale barnacles about prehistoric whale migrations? We'll start, of course, with this first question. And to start answering this question, it was important for me to begin with modern-day whales and barnacles. So if we want to figure out if barnacles actually record anything about where their hosts have been, why not start with the modern day? We've got whales that we know where they're moving, we know what the temperature is of the water, we know what the isotope balance is of the water. So this looking at modern barnacles gives us a nice proof of principle, right? So that's where I started. So here's our barnacle again. And I've already told you the barnacle basically grows downward. And if I sample the isotopic ratio all the way down that shell from top to bottom, we'll get a profile of isotope ratios. And I just want to quickly orient you that time will be moving that way, which is to say that here on the left is older part of the shell at the top, and on the right is newer part of the shell at the bottom. So if I isotopically sample this shell all the way down that growth axis, you get something that looks like this, okay? So real quick, you might see, it's not just a random scatter. There's a peak, there's a trough, there's a clear progression between, okay? And because of that, that equation I showed you, if this is telling us anything about where that barnacle's whale has been moving, then this region, the most enriched or the peak of the profile, should correspond to when the whale was in its summer feeding region. And this region should correspond to when the whale is in its winter breeding region. Now, this barnacle was collected from a whale in the modern day that we know moves between the coast of California, where it hangs out and feeds in the summer, and the southern tip of Baja. So that coast of California should correspond to the light blue, and Baja should correspond to the dark blue in the respective times of year. And now I just simply wanted to ask, well, is that true? All right? So let's take the profile, put it up there. There's our barnacle again, just for looks. And I want to basically kind of look at these two major regions of the profile and ask, do those values line up with that barnacle actually being where we know the whale was, okay? So we'll focus on that top bit first. And I told you earlier, of course, that in the modern, we know what temperature is, we know what isotope balance is, so we can actually map what isotope ratio a barnacle should have in its shell every month of the year based on where it is, right? So this is the map for June in terms of what the barnacle shell should record, and now I'm just going to plot out what region of this ocean can account for those values. And if you can see it, hopefully, the quick answer is that everything that's in light blue is consistent with where the barnacle could have been, which is completely consistent with the barnacle being off the coast of California, where we know it was. So if I move on to that trough, we can plot, all right, middle of the winter, the whale should be off the southern tip of Baja, and here's what our map looks like. And if we ask, all right, well, what regions of the ocean can account for those values I've highlighted? It's right there, southern tip of Baja. Wouldn't show you to you if it didn't work. So completely consistent yet again. And I can summarize that information right here. Here's the same information for this barnacle, showing that, again, the peak and the trough correspond perfectly to where we know the whale actually was. And I didn't go through it all, but if you go stepwise through those higher but not highest values, it's completely consistent with the whale being off the coast of California through the late summer and September, and then beginning to migrate in late October or November. Now, we have also done this with other barnacles that came from different whales with different migration routes. And this, for example, is a barnacle that migrated, or the whale migrated, between Southeast Alaska and Hawaii. Same result. The barnacle shell isotopes are really reliably recording something about where the whale has been. So, first of all, scientifically speaking, this is just damn cool. And then for the PhD student who's hoping that you can kind of add something unique to the scientific literature, this is really exciting because this means that, okay, now we feel we have a reliable method to get some information about prehistoric whale migration. So answer that first question, do barnacle shell isotopes reliably record whale movements? Say, yep, looks good. And we can move on to this other interesting question. Okay, well then, if we feel like we can rely on this method, what can we learn from fossil barnacle shells about prehistoric whale migration? Well, this gives you a quick idea as to what the fossil record of whale barnacles looks like. And as you can quickly tell, there's just some really brutal places here. Italy, Panama, Ecuador, New Zealand, just awful places to have to visit. And I have, of course, as a PhD student, it's been important that I do some field work, and I've been able to go out and collect some fossils. And again, just how, I don't know how this is my PhD work, but this is. So this was my field site in Panama. This is my view at night, and I drifted to sleep listening to the waves of the Pacific outside. Also did field work in Ecuador just this last year. So this is another field site. And it's been just a great experience. This is some of the outcrop in Ecuador. And this sediment has been uplifted over the last couple million years. So what was once shallow sea floor is now uplifted in this wall. And you could walk this beach and just pick fossils out of the wall. And this is me lovingly looking at the first barnacle we found in the field. Actually, Seth, my PhD advisor, found this one, so many thanks to Seth. I was extremely happy. And then in this past year, like I said, I went to Ecuador. This was some of the team that worked with me. Actually, I realized, talking to the other presenters, that we're all Berkeley grads, so I want to apologize deeply for what I've done here. In my defense, I've spent 1 year there, and I only wore the shirt because I knew it was going to get sweaty and dirty. But nonetheless, there it is. I apologize once again. Okay. All right. So we collected several fossils, and came back to the lab, analyzed them the same way that we did the modern day barnacle shells. And from the Panama specimens, these are some of the results that we got. So none of these were complete pretty shells, but some of them were pretty good size. So this is one plate of a shell. And real quick, you can see that many of them have a peak and a trough and a clear progression in between. And we have a trough, a peak, and a progression. And even this one, it's a little bit more flattened out, but there's a clear trough, there's a peak, there's a progression back and forth. And I want to say a few things about these preliminary results. One, and most importantly, is I want to draw you to this little bar over here. So that green bar shows the isotopic range that is recorded in a clamshell, a fossil clamshell, collected next to the barnacles. So that clamshell is recording everything, the full range of isotope values you expect to see over the course of the year in that one place, right? And as you can quickly tell, this barnacle is experiencing way more variation in its isotope range. And the only way to account for that is, of course, that this whale was migrating. And to be even more specific, it was migrating probably to an extent very similar, if not greater than, modern day whales. And that's true for all of these profiles, all of these fossils, even the one that looks more flat. That's still a range of isotopes pretty similar to what several modern whales and their barnacles experience. Another thing is that you might quickly notice all of these look very different. And there's a relatively easy explanation for that. So these fossils came from Panama. In modern day Panama, whales that congregate there in the winter migrate out to very different feeding regions. And so this work just indicates that that has been going on for at least several hundred thousands of years. Easiest way to account for that difference is these whales are moving outwards to different places. During that first bit of work I did, we also analyzed several very small partial fossils from California. So you can tell that's just barely a nubbin of barnacle, but it's still enough that we could get some small isotope profiles from them. And you'll quickly see that these profiles look broken, right? You're just getting a little segment because it's such a small section of barnacle. Maybe one seems to have a full peak and trough and progression, but the others you're just getting a segment. Nonetheless, these barnacles, which represent two different populations of whales, all record ranges of isotope variance that are too great to explain via a whale living in one place. So migration is present in these populations as well. Now, since this initial work, which was a couple years ago, we have analyzed a lot more fossils. And in fact, we've analyzed fossil barnacles from 6 different populations now. And really, I want you to focus on this graph on the right. So this graph is showing for every different group of fossil barnacles that I've analyzed, what's the range in terms of the maximum and minimum that they're seeing in oxygen isotope. And if you look at the far right, that gray is modern barnacles, so that gives you kind of like the baseline. And really quickly, you can see that all of these fossil groups are experiencing ranges of oxygen isotope values that are as great or greater than the modern day counterparts, indicating that migration was present in all of these ancient populations, which are 6 different whale populations from 6 different, slightly different time periods. So in that, we can say that migration seems to be a very long-standing, ubiquitous behavior amongst the giant whales. Now, in the course of doing field work, sometimes you have some unexpected surprises, and this was one. So when I was in Ecuador last year, found this strange little fossil. It was really delicate, so I wrapped it up and just kind of put it in a container and thought I'll look at it more when I get to the lab. And then after cleaning it off, it became really rapidly apparent because of some of these structures, these kind of tubes that end nowhere, and because of the grooves on this shell, that this is a Cryptolepis rationecti shell, and everything else I've been talking about is Coronula diadema, which is the humpback whale barnacle. And if you remember from that brief, quick intro to the barnacle slide, this is a gray whale barnacle, but it's from Ecuador. Obviously, there's no gray whales in Ecuador now. In fact, there's no record of gray whales ever living in the southern hemisphere. So this was a really interesting find that we're kind of working on right now in terms of what we're going to write up about it. And there are several different reasons that any ancient population of gray whales that once lived off the coast of South America is no longer there. The easiest explanation is relatively simple. This is a reconstruction of what the area this fossil was found in was like over the last several 100,000 years. And in the late early Pleistocene, I found the fossil right about here. This region was a shallow basin, very shallow water, somewhat protected, warm, perfect area for gray whales to breed. Gray whales are very, very selective in terms of where they will breed. It has to be shallow, warm, semi-protected waters. Humpbacks are more variable. They'll breed in shallow waters, they'll breed in deep waters. They can do with either. But gray whales are very, very specific. And over the last couple million years, this area has undergone geological uplift. And as that uplift has proceeded, it's completely erased that basin. So it's completely erased any potential breeding ground for gray whales in this area. So again, gray whale barnacle, indicative of an ancient gray whale population living off the coast of Ecuador, and has probably been lost because their breeding area has gone away. So with all of that, let's conclude kind of what we've learned so far. First, barnacle isotopes accurately record whale migration paths. Next, isotopes from fossil barnacles indicate that migration is a long-standing, ubiquitous behavior among the giant whales. And last, Pleistocene Ecuador was home to an ancient lost population of gray whales. So, you probably already know where I'm going next. This is what my research is turning to now. Now we're basically looking to do with the ancient oceans what we've already done with the modern, using several different proxies to try to constrain prehistoric seawater temperature and isotope balance, and then we can begin to map out where these ancient whale populations were actually moving. And that's where we get to the really fun stuff. But you'll have to wait a little bit. Maybe I'll come out for another Nerd Night if you'll have me. So that's coming later. And with all that said, have a ton of people to thank that have helped me with field work and who have loaned me specimens, and have many funding sources to thank that have made the work possible. And I think I have time, so with all that, I'll take any questions if there are any. Oh, good question. No, not all. He asked if all species of whales have barnacles. And quick answer is no, at least not strong accumulations and associations. Humpbacks and gray whales, and to a smaller degree right whales carry a lot. Blue whales, fin whales, sperm whales are usually relatively free of barnacles. So I'll answer both questions. He asked, how do I know if I find a barnacle that it's actually from that area and it didn't like get carried in on a current? Right, so in Ecuador, we spent 3 days on site and we found 96 barnacles, which is an insane number. And the only way to account for that many barnacles being there is a whole lot of whales were there frequently. And then, who asked? The why do not all whales have barnacles? We don't know. One idea is simply that barnacles tend to congregate on the whales that come together in very large numbers. It will help the barnacles breed and find new hosts. And gray whales and humpbacks get together in very big groups every single year. What's that? On the barnacles? I don't know about whale penises, I'm sorry. Barnacles, yes, are very well endowed. Yeah, so he's asking about that map and the fossil barnacles. I've shown where they are. That other one you're thinking of is not a fossil I found. It's a Cetoporus or right whale barnacle. It was unexpected. It was found in the Mediterranean and indicated something about where right whales used to be migrating.
How did you choose the specific field sites that you chose?
She asked, how did I choose the field sites? Luck. One field site had been published on before where people had indicated they found some barnacles there. And then the really lucky one was one of my advisor's collaborators had found a barnacle at the other site, and so we thought, let's just give it a shot, and we found several more. Yeah. Have I found correlations between modern populations and? Yeah, I think the quickest answer to like how have I found correlations between different populations is I need to analyze a lot more fossils because this work, like the modern day work, depended on like 5 barnacles. And so when you're thinking about comparing populations, you really want to get numbers a lot higher before I can make any big statements there.
Let's do one more.
How do you get a barnacle off the whale?
Oh, you wait till the whale is beached. I mean, if you have enough whiskey in you, maybe you jump in after it, but I've waited till the whale's beached.
All right.
All right, thank you very much.
All right, can everyone hear me? Good stuff. Let me just get this attached. All right, so yeah, all three of the speakers are Berkeley Bears, so first of all, go Bears. All right. Okay, so, go to my next slide. Okay, right. So thanks for showing some interest in where some of your tax dollars go and where a lot more of them might go in the future. Okay, so Mars. So why do we care? So Mars has been has had a place in our collective cultural imagination for millennia, ever since the ancients called it the god of war, that evil red eye in the sky. But more recently, as we've sent robotic explorers across the solar system to other planets, including Mars, and as technology has been advancing and as human populations have been rising rapidly, it's become natural to ask the question, when and how will humans venture away from the Earth, not just to visit but also to live? And Mars has become a kind of a natural place to look. It's got a nice 24.5-hour day. You get an extra half an hour in bed every day. It's got seasons. It's got moderate gravity, mountains, valleys, etc. And because humans enjoy things like breathing, it's nice, and drinking liquid water, today I'm going to tell you about an important aspect of any planet that you might want to live on, and that is the atmosphere. Okay, which brings me to the topic of my talk, resurrecting the Martian atmosphere. Why might we need to resurrect it? And the answer is because you were lied to by Hollywood. I know, right? Like, that's a shock. So this is a scene from The Martian. It's kind of hard to see there, but they're struggling through a dust storm. They're fighting against the wind like this. And the Martian atmosphere is nowhere near thick enough to ever do that. That would just never happen in a million years. The ship, tips over, and that's why Matt Damon gets stranded there. Total BS. That wouldn't happen at all. So this isn't real, but someday this might be. This is a artist's impression of a city on Mars with your launch pads there, etc. And so since that might be real, it's important to know about the atmosphere. So let me tell you about how Mars's present atmosphere and climate. So it's mostly CO2, poisonous. The pressure is less than 1% of the pressure in this room. So even a really, a hurricane wind would just feel like a little light breeze there. It receives a lot less solar energy than the Earth does, between 50 and 65%. So it's really cold there. The average temperature at the equator is about minus 76 Fahrenheit. At the poles, minus 180 Fahrenheit, very cold. And liquid water is not stable on the surface. If you were to pour a glass of water on the surface of Mars, it would boil away, not because it's warm, but because the pressure is so low. So the TLDR is thin, cold, dry, and poisonous. So none of those things are good. And also too thin to stop the cosmic rays that are always hitting every planet's atmosphere from giving you all sorts of cancer. So bad news today. Okay, was it always like this? Nope, certainly wasn't. How do we know that? We have several lines of evidence from orbit, and this goes way back to the 1970s. We've seen these flood-carved channels, these areas where there were these mega floods with billions of cubic meters of water. They've etched out these features on the surface here. We've also seen places where there was clearly a lake inside of a crater, just here. The crater down burst, the water, flowed out along the surface here. And lastly, we have these sort of dendritic, rain-carved valley networks where you have this sort of spidery pattern that we see all the time on Earth. If you're in a plane, just look down sometime and you'll see where rain falls on a mountainside and all flows down into rivers. So we've seen that from orbit. And then the rovers have also seen a bunch of other evidence as well. Different examples are certain kinds of stone that can only be formed by long-lived liquid water. So-called mudstone was seen by the Curiosity rover, the Opportunity rover. So these so-called blueberries, it's a mineral called hematite. It's only formed in long-lived liquid water environments. Same thing with the layered terrain that the Opportunity rover also saw here, where you have these layers which are laid down in riverbed environments, and things called underwater sand dunes as well, called, I guess the geologists call them festooned cross-lamination. So there's this stuff, hydrated silica. There's all these things that can only be explained by long-lived liquid water. So there was definitely thick atmosphere, warm planet a long time ago to allow all this liquid water. So where did it go? Where did the water go? Where did the CO2 go? Well, since surface water isn't stable at Mars's current pressure, like I just said, and even at higher pressures, it's too cold right now to explain that. So there must have been thicker, warmer atmosphere, like I just said, but where did it go? Could have gone up, could have gone down. Down, we do know that volatiles, i.e. water and CO2, can go into the crust, and we have meteorites that have arrived on Earth from Mars, and we have seen carbonate minerals in those meteorites that show that some of that CO2 was absorbed into the crust. And we've also seen that those same volatiles can be lost upwards to space, and this is just an animation of ions being stripped away from Mars by the solar wind. I'll get to that more in a minute. Okay, so let's look at the down part. Some of these volatiles did go down, and this is a map of all the different places on Mars where we've seen minerals that have been created by liquid water. They've got different names here, but you can see all these different colors, and you probably can't see because it's kind of hard to see, but carbonates are in green. There's hardly any carbonates here. So of all the places on Mars, we really don't see a lot of evidence that the CO2 went into the ground. Maybe at most, you might have 20 to 50 millibars, i.e. 2% to 5% of what we'd actually need to get an Earth level of atmosphere back. So let's look at whether it could have gone up either. So since 2014, NASA's MAVEN orbiter has been exploring atmospheric escape from Mars. This is an animation here showing the view from MAVEN on the right and the orbit on the left. And the idea here was that the MAVEN's orbit takes it close enough to Mars to measure the processes happening in the atmosphere, where the atmosphere is being torn away from the planet by the solar wind, but far enough away to get a global view of the escape. And I'm not going to go into this in detail, but multiple different physical processes can cause atmosphere to escape in the form of ionized particles and in the form of neutral particles, and this is just a cartoon of all those different things happening. The TLDR here is that the picture is complicated, and scientists, me included, are still working it out. All right, so one interesting thing, though, is that we've seen that these escape rates increase when the sun is brighter in the UV and when there are solar storms happening. These are things like solar flares, coronal mass ejections, where the sun belches out billions of tons of hot gas and it rushes across at 1,000 kilometers per second and can tear atmosphere away from a planet. And one thing we saw here, this is the extreme ultraviolet versus the escape rate, and you can see there's a positive trend here. There's a paper I wrote a couple of years ago showing that the brighter the sun is in the UV, the higher the escape rate. Now, but what is the history of the sun's ultraviolet? Turns out it was much brighter in ultraviolet 3.5, 4 billion years ago. This is a plot here showing that same ultraviolet flux against the age of the sun. We know this because there's other stars that are the same type of stars, so-called G2 type stars, and we can see how bright they are as a function of their age. And we can see that the sun was probably 6 or 10 times brighter in the ultraviolet 3 or 4 billion years ago. So when you do the math, you sort of integrate all that loss back in time from what we know now, several hundred millibars, certainly close to a full bar of atmosphere, a bar being what we're experiencing right now in this room. So we've lost a lot of atmosphere. There's not a lot of obvious CO2 in the rocks. So what can we do to get the atmosphere back so that humans can go live there? Okay, so let's get started. Okay, what do we need in order to do this? Number one, and I can't stress this enough, a fanatical will to succeed. People on Earth are not going to care about putting in the work to make Mars livable. Only people already living there, Martians born there, are going to give a shit about making their atmosphere, because it's going to be really expensive, which I'll get to. Robots, well, hopefully, wait, humans, but people or robots living there are going to be the ones to do that. Second thing, just all sorts of money, just so much money, bajillions of dollars, a lot of money, probably more than $1 million even, much more than $1 million. I just took a wag, several trillion. It's probably way more than that even. Okay, third thing is energy, so much energy to create the atmosphere. Wind is not going to cut it, not enough energy density. Solar panels, this is Matt Damon again, not going to cut it. Nukes, lots and lots of nuclear power plants, nuclear energy, thousands of nuclear power plants, probably fusion ones built on Mars, and I'll get to that more soon. So just buttloads of energy. And a lot of patience, like your grandkids, your great-grandkids might just see the beginning of this type of thing. So this isn't going to happen fast. And lastly, a large quantity of the right elements to actually make an atmosphere readily available. Not just the elements that we can breathe, but the elements that will create enough of a greenhouse effect to warm the place up. And we don't know if these are available on Mars, and I'll get to that in a couple slides as well. Okay, so let's go through the steps. So we'll go through the steps now that we need to do this. The first thing that we could do, the kind of easy one, the kind of gimme, relatively speaking, is to melt the dry ice. So Mars has a lot of CO2 ice locked up in its polar caps. If we were to raise the temperature of those polar caps by a few tens of degrees, we would get sublimation. So essentially, it would just sort of evaporate off the surface of the polar cap here. That would lead to higher CO2 pressures, an increased greenhouse effect, higher temperatures, and more sublimation. And in that way, we can probably get 12 to 14 millibars. So we could kind of triple the atmospheric pressure from what it is today, but we're still like less than 2% of the way there. So not really going to do it. But that would be the way to start. Where would we even get the heat to even do that, though? I mean, one thing we could nuke Mars, which Elon Musk has often talked about. The colonists might not like that. They might have an objection. We could dig these things called moholes, which are in, if anyone's read Kim Stanley Robinson's Red Mars book, you could just dig these holes, 5 miles deep, a mile wide, and at the bottom of them, at the so-called moho boundary between the crust and the mantle, it's really hot down there, so they would release hot air constantly. That could help to heat things up as well. You could put fusion power plants at the poles to melt the ice. You could put orbital mirrors to concentrate sunlight down to melt the ice. Okay, but let's say that you've done that and you've tripled the atmospheric pressure. You still have a long way to go. Where are you going to get the raw materials to build your atmosphere? And one way to do it is to just dig up all the raw materials from the ground. We don't tend to think of air as being heavy because we can move through it. But every square meter of Earth's atmosphere, if you just took a square meter and go all the way up to space, that column of air weighs 10 tons. So you need to dig up 10 tons for every square meter on Mars. And there's 144 trillion square meters on Mars. It's got the same land area as Earth does, actually, which is an interesting little factoid. So you need to dig to an average of 3 meters over the entire planet. That's 1 million billion tons of rock. And that is a lot of rock to dig up. And I was wondering, well, how much is that? How much is 1 million billion tons of rock? It's a lot, it turns out. To take one example, the longest tunnel ever built by humans is called the Gotthard Base Tunnel in Switzerland. 35 miles long, it's 1.5 miles deep, took 22 years, $13 billion. That was 60 million tons of rock. So you can repeat that 17 million times at a cost of $20,000 trillion. And then you've just got the raw materials to make the atmosphere. You still haven't actually made the atmosphere yet. You've just dug it all up. So if you do that, you might be able to tease out the additional 4% of CO2 that's kind of adsorbed in the regolith, but that's down to more like 100 meters, so you're probably not going to bother doing that. So that's not really going to work. More realistic is to liberate the oxygen, hydrogen, carbon, nitrogen, which is locked up in all those minerals that you've dug up, by vaporizing those rocks and then releasing it, so by building atmosphere factories. Okay, well, how do we do that? How do we actually do that? How do we vaporize 1 million billion tons of rock? No big deal, right? Yeah, easy. Okay, so 1 ton of rock takes about 3 gigajoules of energy to vaporize, and a big nuclear reactor is about 1 gigawatt. So every 3 seconds, a big nuclear reactor could vaporize 1 ton of rock, or about 10 million tons per year per nuclear reactor. Okay, that sounds like a lot, right? Okay, no big deal. We just need 10,000 nuclear reactors, which is equal to Earth's entire electricity output, running for 20,000 years. That's how much energy we would need to release. And that's like a lower bound, by the way. It's probably factors of a couple above that. I just wanted to take sort of a stab in the dark at it. So yeah, not happening anytime soon. Okay, some people say, okay, fine. Well, that sounds ridiculous. But what about comets? Can't we go redirect comets? They've got a lot of water. They've got nitrogen, etc. Okay, well, we could. There's again, turning to sci-fi. You could turn ice to steam inside a comet with another nuclear reactor and blast it through a funnel to kind of steer it as a rocket to kind of steer it towards Mars. Okay. Comets weigh between 1 billion tons and 100 billion tons, so we need to crash about 10,000 to 1 million comets into Mars to get the kind of water and other elements that we would need. That's impossible. Too many for humans. We would need autonomous robots that would build copies of themselves, navigate themselves to these things, bring the nuclear reactors, set everything up. And like autonomous in-space assembly and navigation is just barely starting. We're hundreds of years away from being able to do any of this. And even once we can do it, it would take hundreds of years more, if not thousands of years, to get this many comets. Okay, let's say that we do all that. So what gases are we going to look for? CO2 is a pretty good greenhouse gas, as we sadly know on Earth. Dark joke. It's good to get things going, but it's actually, A, there's not really enough of it, and B, turns out that when you run the simulations, once it gets above about 100 millibars, it actually isn't very good. It actually turns down in terms of its greenhouse effect. Oh yeah, and it's poisonous to people, so not good. Oxygen, there's plenty in the rocks, but you don't want an atmosphere that's too oxygenic, I guess, because things burn in oxygen. You don't want to set the atmosphere on fire. Nitrogen would be great, because our atmosphere here on Earth is 78% nitrogen. But there's not a lot of nitrogen on Mars, sadly. There's a little bit. Some might be deeper below the surface where we've not seen it yet. Doesn't look good, though, for nitrogen. Okay, now, how do we actually heat the planet up? Assuming that, we didn't build enough of those moleholes, can we have a greenhouse effect? We need a 70 degrees Celsius greenhouse effect. It's a big one. Earth's greenhouse effect, like how warm our planet is compared to how warm it would be without an atmosphere, is like 20, 25, something like that, degrees Celsius, way bigger greenhouse effect. CO2 is not great, as I just mentioned. Methane, a lot better, 84 times more efficient, but it's super poisonous to humans, and even that's way too much to make practically, given how we know how to make methane. There is this like fancy super greenhouse gases that are based on fluorine, where you'd only need about 0.00002%. So that actually might work. I'm not going to read all these, but there's a bunch of different chemical compounds that might work. So this is the one part that's not as ridiculous. This actually might be doable. Okay. Not that we've gotten ahead of ourselves already, but let's not get too far ahead of ourselves in general. Okay, so prerequisites to even starting this process. Let's just send humans to Mars and not kill them. I think we can do that. Get them there, get them back, don't die. That's step one. Then send humans there to actually live in a little outpost, a compound. Let them learn how to deal with the radiation. Let them learn how to deal with the recycling of water and the making of air from resources. Let them try planting things that are at least partially in Martian soil, so we can have some sort of a sustainable ecosystem. And let's do that first. Okay. And then, this is the one that I think is the really hardest one. Establish a society large enough and big enough with folks who actually care enough to start this. Like, how are we going to get from 10 people to 10,000 people or 100,000 people? And Elon Musk has his ideas about, selling tickets, etc. So this is a really tough part here too. We have to wait for enormous technical advances in, space travel to bring things cheaply from Earth, so it's not hundreds of millions of dollars to send a single person. I mentioned earlier, figure out how to let robots build copies of themselves, assemble themselves, figure out where they need to go, because currently every spacecraft navigating the solar system has a whole armada, or that's not a good word, crew of people on Earth who are telling it exactly where it has to go. Once robots learn how to do this by themselves, then maybe we can get there. As I said, I'm steering comets. Same thing with industrial production and mining. It all has to be done by AIs, and because there just aren't enough people to do this, and then figure out what those right gases are, i.e. geoengineering. The question is, is this going to be hundreds of years, 1,000 years? When will space travel and supporting the colony really get cheap enough? The price tag has to be right. And like I said, supporting the colony, people on Earth have just low tolerances for spending money that doesn't help them personally. We all tend to be selfish. How can we, when are we going to be able to fix medical problems inherent to living on Mars? If you live on Mars, you're going to have to live underground most of the time because the radiation will give you cancer. So maybe we can learn how to fix that, DNA damage, so that'll be important too. How can we get that society to be large enough to grow to the kind of size that we need? And questions of how is it even going to run? Is it going to be capitalism or collectivism, socialism, communism? Do you make people pay for their air? That sounds shitty. I don't want to do that. Are they going to want independence from Earth? Is there going to be conflict between Earth and Mars? Again, I'm veering into the realm of science fiction here. Are the Martians going to sort of resent the Earthers coming in with all their money, whatever, and like taking their jobs and stuff like that. So there's all sorts of things to deal with on that sense too. The right raw materials, as I mentioned earlier, do they even exist in sufficient quantities? Like I said, it'd be great to have nitrogen, but we don't really see much of it. So does it exist deep underground? Can they really be extracted? Are they just too deep to get? Can we ship them from Earth or elsewhere? I mean, again, going to science fiction, but Titan's atmosphere, that's the moon of Saturn, that's all nitrogen, so we could ship it from there. But I mean, shipping 1 billion tons of it, how long until that can be done? So just to sort of wrap up, talk about the big picture here. In summary, I think with just colossal amounts of cumulative will, money, time, technology, it is possible, I think, to make Mars habitable for humans, but people talk blithely about how easy it's going to be, and folks like Elon Musk say, "Oh, it's simple," and it's just not. So don't believe him when he continually tweets that. There's a lot of unknowns. There's the unknowns that we know about, like whatever the whole nitrogen thing. Then there's all the unknowns we don't know about, like what are all the things we don't even know to fear yet. So the timeline is somewhere between hundreds of years, really, really optimistically, and maybe never. So I guess to finish off, watch this space and have your children and your grandchildren and your distant descendants also watch it too, because it's going to be a while. Thanks, everybody. Questions? A couple of reasons. First, the question was, why does Earth have an atmosphere? Or why do we keep our atmosphere? Two things. One, Earth is continually outgassing from volcanoes, and so there's a source of oxygen and other things from volcanoes. Second of all, Earth has a much higher gravity than Mars, so Earth is able to hold on to more of its atmosphere. Earth is losing atmosphere, mostly out the poles through processes involving strong electric fields. So Earth is losing it, it's just not losing it faster than it's outgassing it. Any other, over here? I haven't personally heard any, but I mean, with things like CRISPR and stuff, I mean, who knows what could happen in a while. I think you could do that. You could have people who are more tolerant to radiation, who could maybe breathe at lower atmospheric pressures. Yeah. Again, I mean, sci-fi tells us that. Here. Okay, so the first question was concerning the ethics of terraforming Mars, and again, going to science fiction, but the Green Party on Earth, its equivalent would be the Red Party on Mars. The people who don't want Mars to be changed too much. Oh yeah, this is a thing in sci-fi. Yeah, it's true. Sadly, I think that people care about the Earth because they're here, they see the beauty of nature, and they're willing to fight for that. I don't see people being willing to fight that. I mean, some people will. There might be eco-terrorism. I just don't see it as being as strong as it is here. The second question was concerning whether you could just build megastructures on Mars that would have their own self-contained ecologies and atmospheres and et cetera. Those an option that would not sort of spoil the planet as much. And what I'd say to that is, sure, it'd probably be easier to build them tall because of the gravity. Yeah, that would be a way of getting around all the impossibility which I laid out here about actually making a new atmosphere. If you're willing to live in domes, sure. Yeah, but I mean, eventually people are going to want to, walk under a sky and breathe normally. One more, yeah? Sorry, what? Oh, to Venus. Well, the surface of Venus would crush you, burn you, and dissolve you in seconds. So maybe living in the clouds of Venus. Yeah. like 50, 60 kilometers up from the surface of Venus. The temperature is pretty much what it is in this room. The atmosphere is so thick you would float with like cloud cities like in Star Wars. There's been some NASA work that's looked at the kind of concept of living in cloud cities on Venus, but I don't know. It sounds even crazier than this. But maybe it isn't. Maybe I just haven't looked at the math yet. Last question, yes? Yeah, that was kind of the point of my talk, is to, yes. Sorry, that sounded condescending. That's not what I meant. But yes, I was just laying out how incredibly difficult this is going to be and how nobody on Earth is ever going to care about spending this much money when we have so many problems on Earth. The only people who are going to care are the native Martians. They'll care enough because it'll be their home. We have our home here, and we should take care of it. Okay, thanks.
Can you answer more questions at today's stage?
Sure, yeah.
We're going to take a quick 7-minute break. The food's sold out, the OPL is still here, and please get another drink. We'll be back in 7 minutes with our final talk on Chevron.
Yo, yo. Okay, there we go. Well, thank you, everyone. I think that it's really important that you guys give yourselves a round of applause for coming out tonight, staying. Awesome. Thank you so much for having me. That is very true. I did my dissertation on the development of Richmond, looking at the relationship with Chevron. So some of the juicier tidbits, the more sinister acts of Chevron with using greenwashing tactics to mitigate environmental harm and hazard is another talk. Today's talk is something more discreet, more subtle. So let's dive into it. I feel like I should give you a little caveats too. This is purely only one chapter of my dissertation. There were many chapters within it, but I'll save you the boring theories and jargon that are entitled for getting a doctorate. So enough of that boring snooze cruise introduction, and let's start this booze cruise. So cheers, everybody. Let's dive in. Right on. So when we look at a map, what can we really see? If we peel back the layers of history, talk to the community, you'll see something different completely. So when I was doing my dissertation, I aimed to peel back these layers of history by meeting with community groups, meeting with residents, holding focus groups and interviews, and doing archival research to get deep down into that history. Richmond, as we know it today, arguably stems back to the Atchison, Topeka, and Santa Fe railroad station. Sorry, I'm last, which means I have had a few drinks, so bear with me. Yeah, thank you. This row that's clapping, take a sip for yourself. The railroad itself and the terminus in Richmond was built just before 1900. And I argue that that's almost the foundation of Richmond itself. And why, you might ask? In 1900, Standard Oil purchased the Pacific Coast Oil Company. And Rockefeller at the time dominated the oil market. He manipulated railroads, and he commenced his own version of manifest destiny by bullying and buying out small oil producers across the country as he made his way out west to areas including Richmond. So after that merger between Pacific Coast Oil Company and Standard Oil itself bought over 100 acres of filled marsh, tidelands, and flatland in Richmond, and immediately broke ground on construction on the oil refinery in October of 1901. It was completed and operating not even a year later, by July 1902, less than a year later. And if buying out oil producers across the country and bringing it via rail to Richmond wasn't enough, Rockefeller built a new pipeline that connected the refinery to the burgeoning oil extraction in the Central Valley of California in 1903. So just less than a year later, 1903, and prompted the development of a nearly 200-acre storage site called the San Pablo Tank Farm. Can you guys say that with me? The San Pablo Tank Farm. This will be important for later. This land was acquired in the northern part of the city. So, sorry, there's a little lag. So as you could see, Chevron Richmond, as we know it today, acquired this much property along with the San Pablo Tank Farm in the northern area of the city. And as you could see with the city as a whole, that Richmond is kind of the same size as the refinery itself, but less so if you include other properties that it acquired. So following the railroad and the construction of the refinery, industrial activity beyond the refinery moved in, which prompted the incorporation of the city of Richmond 4 years after Standard Oil had built the refinery in 1901. So this chicken and the egg argument that's really popular in environmental justice communities, it's no debate here. The refinery was here before the city was even a city. And once the city became incorporated, more industries came flooding in. So throughout the 1920s and the 1930s, a downtown emerged as shops like Wine Haven came, as American Radiator came in, the Ford Motor Company, the Kaiser shipyards. It was so much growth that by 1940, Richmond's population had jumped from just that mere 2,000 in 1905 to nearly 24,000 in 1940. And 1% of that population was relegated to a 4-block area in the northern part of the city. And it's not that 1% you're thinking about. It was the 1% of African American residents who lived in the area. And before World War II, comprising 1% of the population, they were spatially and racially segregated, but the area at the time was multi-ethnic, with Italians and Portuguese who intermingled, and it was a more joyous time before World War II. And World War II drastically and radically changed Richmond. I am talking from 1940, a population of 23,000 to over 110,000 in less than 5 years. Staggering growth, an influx of immigrants and migrants from all over the country trying to take advantage of wartime opportunities. People from around the world hoping to get into this market. A large part of this was actually the Kaiser shipyards. And the Kaiser shipyards were actually one of the most producing wartime areas because of the amount and rate in which they could produce and send out ships to war. And so these wartime years in the early to mid 1940s was actually the only time in Richmond's whole history in which Standard Oil, Chevron Richmond, whatever you want to call it, was the main employer. So a very short period in which the refinery was not the main employer within the city. And the second Great Migration was really important because it expanded that area, that 1% that we know as North Richmond. But what happened was no municipal government, not the city of Richmond, no federal government would step in to take responsibility for this area of North Richmond. And today, it remains unincorporated, ignored. Oh my gosh, my drink. I'm not ignoring you. And so during this time, again, with this massive influx, this quintuple of the population growth, a number of federal government housing projects were built. Local housing authorities also provided wartime housing, but it catered largely to the white population that was coming in, the Okies. So over 80% of that subsidized housing to meet with the people who were part of this wartime economy, only 80% of that housing was going to whites, 19% were going to the blacks who were moving in. And because of this discrimination, and discrimination in loans, in the realty market, just overt racism across the board, that area of North Richmond grew with the population resorting to their own methods of having to build houses, from industrial scraps from the Kaiser shipyards and the other industries like the Ford Motor Plant that had moved into the area. And so these houses not only violated building codes for safety, but also sanitary guidelines. And what's even more is this area, North Richmond, was in floodplains. So when the rains would come, the areas would be flooded out, and residents talk about growing up and taking a boat from their house to get to school. By this time, the 50s and 60s, racial tensions and animosity were growing in the area. Riots were breaking out across the high schools in Richmond. And one of the largest protests in Richmond was the protest with the Black Panthers after Denzel Dowell, a 22-year-old unarmed North Richmond resident, was shot in the back 6 times by a police officer. It was one of the first times the Black Panthers brandished machine guns on the streets. You might imagine this caused more tension, more animosity. And with this growing civil unrest, the white middle class started moving out of Richmond. But so too did the black middle class. One such place that the black middle class was moving was Parchester Village, a development just north of North Richmond. And it was imagined to be an integrated suburban community by white developers eager to provide housing for an emerging black middle class in those post-war years. But as you might imagine, that reality never came true. It became a solidly black middle class area. And so as this movement of different races and classes were moving out of Richmond, North Richmond became even more segregated. It was concentrated with even more poverty. And so the projects of North Richmond were deemed the homicide capital of the United States because gangs, drugs, crime became so rampant. And it's still an issue that plagues the area today. So we could see this area of North Richmond that I was just discussing, the area of Parchester Village, and also area where the black wartime housing was created is in this area, the Iron Triangle. Could anyone guess why it was called the Iron Triangle? Railroads indeed. So as Rockefeller was making his way out west and bringing oil in, so too was oil coming in this area. So this area right here is completely surrounded by railroads that are bringing in oil to the Chevron Richmond facility, and also the 4 other oil refineries that are just north, some of which might burn in this fire that's burning right now. And as you can see, some residents call this the Black Crescent. It is an area that blocks the rest of the city, the wealthier, the wider areas of the city, from harm and pollution and hazard from the facilities at Richmond, or at the Richmond refinery. And in the 1970s and 1980s, as civil unrest was growing, Chevron decided to turn the San Pablo Tank Hill into the Hilltop Mall. So a hill that was nearly 200 acres, holding unrefined petroleum, ancient dinosaurs that did not intend to be put in cars. I couldn't find any information on how this land was remediated from environmental hazard and exposure. The Chevron Land Trust converted the San Pablo Tank Farm into the Hilltop Mall and surrounding offices, commercial space, residential housing, and light industrial spaces. But when this process didn't happen overnight. Debates and negotiations happened with the city for guess how long? 20 years. Someone said 20 years. Any other guesses? 10 years. You take a shot, sir. 10 years indeed. And over nearly 10 years of negotiation between the Chevron Land Trust and the city of Richmond, there was a lot of bullying, lots of fighting. The city council felt like they were paying a lot out of their own pockets for road work, public safety, and other services for such a development. And so they were trying to use the permitting process for a point of leverage to gain and secure provisions from the city, for the city from Chevron, especially because they felt that such a company who was exploiting them in return for their own health, for the Chevron's profit, that they could get a little more, but Chevron often threatened to terminate this project. But one of the outcomes of these negotiations was the Richmond Parkway. It is a parkway which connects Hilltop to other interstate highways and connects the city of Richmond to other areas in the Bay. How many of you have driven on Richmond Parkway? I see a number of hands who have gone up. When it was first proposed by Chevron in the city, it was originally dubbed the Richmond Bypass. What a name, right? Residents of North Richmond, after this long history of exclusion and marginalization, said that this degraded them even further. You're going to bypass us? How rude, considering that they're still unincorporated today, which means they're excluded from legal participation in these negotiations. So this city doesn't even have a say of what happens to them. And going even further, a lot of residents in Richmond believe that the Hilltop Mall development was a project that was a deliberate attempt to break apart the growing Black mobilization in the city of Richmond. And regardless of if this is true or not, we know that this development, Hilltop Mall, pulled white businesses from the downtown of the city of Richmond, like Macy's, for example. Once large business anchors that made Richmond thrive as its own city within the Bay, moved up onto this hill. And as these businesses moved to Hilltop, businesses run by people of color lost foot traffic and eventually lost their businesses completely. And Richmondites today explain that this truly caused the death of downtown. And residents today remain calling it a ghost town as they struggle to invest and bring in businesses to have it be the thriving city that it once was. So residents like this one express that the city was redeveloped with money from Chevron, and then they turned us into a suburb city. Again, going into residents' conception that Chevron was trying to dismantle mobilization against the company to pacify resistance so they can continue exploiting. And as time went on, Hilltop Mall was isolated up on the hill, but they started reducing bus access for essentially non-white residents, the areas of Iron Triangle, of North Richmond. By denying them access to buses, they were denying them access to malls and businesses and other services that were available at Hilltop. More protests proceeded, and ironically now today, with redevelopment efforts, Hilltop Mall is now called the Shops at Hilltop, and they're now bringing in businesses to populations that it once denied with the introduction of businesses like 99 Ranch Market. So again, if we look at the map, we see Chevron, its former Tank Hill, which is now Hilltop Mall, with the Richmond Parkway that moves alongside the historic Black Crescent, which remains today. And this history is not lost. Residents today, as they talk about one another, is excruciatingly painful to hear. We hear residents talking about not going beyond 23rd Street. So the segregation continues today. It is rampant, it is vocal, it is loud, and you could feel it and hear it in the echoes. You could also see a division between the white working class and more elite whites up in the hills of El Cerrito and Richmond with Wildcat Canyon, with the division with San Pablo. And as you might imagine, Chevron plays into these segregations that they themselves helped invest in. But that's another talk that you might have to talk to Scott for to bring me back. And as we conclude, I'll have two fun facts for you. One, North Richmond, even though it has been denied for so long, The community has band together so much and time again for political power, for political voice, that they're actually the first community in the entire Bay Area to have a neighborhood council, which is very cool, very exciting. They have mobilized and achieved a lot by doing so. And then another fun fact to close this off is before Martin Luther King was assassinated, he was on his way. I am not sure the duration, it just in all the notes says he was on his way, so I don't know if he was like on a train, literally on his way, to Richmond to speak about the Denzel Dowell protest. So thank you so much, and I open the floor to questions, and thanks for having me here today. Cheers to you all. Yes. Yes. Point Richmond. So let me come back to the map here. Point Richmond is right here. It's a very interesting, so going back to these play on words with the 1%, the 1% as we know it today as rich entitled whites is the analogy that Richmond residents use to talk about people in North Richmond, where these are typically composed of white middle class residents who have moved in from other areas, including other areas in the Bay because they have been moved out because of gentrification, though themselves are white middle class. But they are also advocates of the environmental justice movement in the city of Richmond. If any of you follow Richmond and Richmond politics, they're one of the most progressive hotbeds in the United States today. And a lot of that is because of the activism seen by residents in Point Richmond. Yes. Mm-hmm.
Earlier, I was really excited to talk to you specifically. Earlier, I wanted to say here, where you said, it's reserved, there's no such thing.
Mm-hmm.
I am excited because I believe academia can voice up to people, but I'm curious to know if that's the approach and attitude you took to interview Richmond residents.
I hosted so voicing up for Richmond residents is the question. I worked at a research institute called the Environmental Health Social Science Research Institute, in which we partnered with community organizations based in Richmond and helped them develop low-cost science tools that would demonstrate environmental hazard and exposure, and we would use those scientific findings as science to back up the ethnographical research that we conducted with residents. So we used scientific instruments along with community organizations and organizing to help them in their efforts to fight for environmental policy with the Cal EPA and with negotiations with Chevron. Additionally, I hosted a number of focus groups with community organizations to help them receive grants and financing for their institutions through bodies including Chevron themselves because of the expansion project in the late 2010s. There was $10 million allocated to community organizations, but there were lengthy processes in which community organizations had to go through to receive those funds. So I worked to try to help community groups who wanted to receive funding from that pot of money to receive those grants. Yes. Sorry, what was that? So Richmond residents have often talked about how at night the city smells different than during the day. So there's often an understanding, which may or may not be true, about hazard happening at night. If it's not visible, it's not happening, right? So they have so there's that thing. Chevron itself has been under probation from the federal EPA time and time again for shady, seedy things such as air monitoring devices that are set up by Cal EPA, federal EPA. When they come to do an inspection, they see that Chevron has set up piping to move the affluent, the emissions, away from the monitors so that the spikes won't show. So that's two seedy things. And the third seedy thing that's more discreet but aggressive is a number of tactics that they employ to prey off of the most vulnerable, to buy residents. And so they'll fracture the community and turn the community against itself in order to bolster support for the refinery. And so there's a lot of dependency tactics that they employ, which are very rude, to say the least. Yes. Yes, I can. For the sake of time, I cut out a lot from this talk. Like a good haircut, I may or may not have cut out too much. But in the 1980s was the beginning of the environmental justice movement in the city of Richmond, starting with the West County Toxics Coalition, which was founded by Henry Clark. And as you might imagine, it was based in North Richmond. So it was a black resident who galvanized the youth in some partnership with the Black Panthers to mobilize the community, to educate them about environmental hazard and exposure, to educate them how and why so many of the residents have asthma. And they mobilize and fight when they can. It's usually through permitting processes points, because those are like the only points of legal contention that they have the ability to actually leverage in, sadly. But those community groups, including Communities for a Better Environment, and ACE, and APEN, they work diligently in the communities, and I highly encourage you to look them up. They're still very active within the community. And yeah, so that's like the history of it. It's still rampant today. Basically, sadly, when it comes to the environmental justice movement, the successes are incremental and they're small because of the power that corporations hold. So going back to Saya, who has already left, voice up, speak up, be an ally. Demonstrations really do make an impact. City hearings make an impact. How many of you knew that there are 5 oil refineries in the East Bay? Okay, so like less than half of you. Every time that there is a point of contention legally, you'll usually see, like for example, a few years ago with the Chevron modernization project, all of you who have rode BART saw all the Chevron advertising, right? A few years ago, 2015. When you see those kind of tactics and antics, that means something's up. Do yourselves a favor, look what's going on locally with these large-scale polluters. It's the largest, this refinery, the Chevron refinery, is the largest greenhouse gas emitter in the state of California. And it's in your backyard too. This is one air basin. So going back to the Mars talk, are we going to pay for air? We don't, but we are paying the cost in our bodies. Stand up and speak up.
Let's hear it for Mia.